So in this video we're going to look at absolute value functions. We'll start with the definition and then we'll do transformations like we did in the previous section. And then from there we'll solve equations and inequalities. And the inequalities are a little tricky, but we'll look at those when we get there. Starting off with the definition of an absolute value, you may remember just sort of in terms of pretty straightforward math, if we have the absolute value of 3, that would be 3. If we have the absolute value of -3, or whatever is in the absolute value, we take and make positive, and so that would also be 3. What that means practically in terms of a number line is when we're talking about the absolute value of 3 or -3, they're the same thing. The absolute value gives the distance from the origin, but it doesn't, the sign doesn't matter for going left or right. And so here, like when I put in 3 into the absolute value, if we thought this is a y equals, the output would be 3. If I put in -3 into the absolute value of x, the output would still be 3. And so we get this kind of V-shaped function. In terms of piecewise functions like we saw in the last section, you can define the absolute value as a piecewise of everything greater than or equal to 0 being y equals x. So we just get that 45-degree line right there. And everything on the other side, the negative side being -x, so that has a slope of -1, still intercepting at 0. So there's a definition for absolute value. And again, what it means is it's the distance from 0 on the number line. So whether it's 3 or -3, it's still 3 units. So this is going to be what we're going to call a parent function. So this has no transformations. This right here is just y equals absolute value x. And what we can do with that is like we did in the previous section on just transformations in general, is we can do all of our shifts left, right, up, down, our stretches, our compresses, and our compressions, and reflections with this function. So let's take a look at, this one is actually right where we left off in the transformation section, so just as kind of a refresher, we are listing the transformations in the order in which they're applied. So if we thought about putting a value in for x, the first thing we would do is take away 2, and you might remember that -2 on the inside means it's going to go right 2, and so that is right there, letter C. And the next thing we would do is we would take the absolute value and then multiply that result by 5, so that's a stretch of 5, which is vertical stretch by a factor of 5, that's F. And then lastly, we're going to shift it down 6, which is E. So same transformations we saw in the previous section, but now we actually have a function that we'll be working with. And we'll do this several more times during the quarter with different functions. This next question is asking us to write the equation for this absolute value. So for this, it's helpful to think of, to take a look and kind of see what happened to it. We have, change colors here. It's our regular one. Let me actually draw that in here. A regular parent function, not doing a very good job of drawing a straight line, but anyhow, it goes over 1, up 1, over 1, up 1. For this one right here, if you notice, let's see if I can zoom in a little bit more, it's going over 1 and down 2. So that means there's a reflection and there's a stretch of 2, because it used to be when I put in 1, I would get out 1. Now when I'm putting in that equivalent, I'm getting out twice as much, or 2, and it's opening down. So that tells me there's going to be a -2 in front of the absolute value. So that's our stretch and our reflection. Then we have our x, this shifted left 1, so that would be a plus 1 on the inside. And it's shifted up 2, so it should be a +2 on the outside. For this one, looks like it's going over 2 and up 1. And with absolute value, you can really think of that stretch as a slope, as the new slope. So in here, the slope was, if I'm trading it on the right-hand side, it's opening down to a slope of -2 on this side, +2 on this side. but you can see the reflection, so that's why we have the negative. On this one, our slope would be, it's running 2 and going up 1. So in other words, when I used to put in 1, I would get out over 1 up 1. Now I'm only getting out over 1 up a half. And so that's going to be my stretch there. So here we'd have g of x, and then it's going to be 1/2 absolute value x, and this has been shifted right 2, so that'd be a -2 on the inside, and down 1, so a -1 on the outside. For these next ones, they're giving us a verbal description of what to graph. So we're going to do absolute value shifted left 5 and up 2. So starting at the origin, we're going to go count left 5 and then up 2, and that's the new vertex, that's the new pointy part. Absolute values are mercifully easy to draw, so it's just, if there's no stretch, it would just be over 1 up 1 over 1 up 1 on both sides forever. So that would look like that. For this one, we're supposed to reflect across the x-axis, shift right 6 and down 5. So let's go right 6, down 5 would put us right there. And then from there, we don't have a lot of room to draw it, but it would look just kind of like that. And then opening down because of the reflection. This one is stretched by a factor of 4. So if we think of our regular one, it would look kind of like that without any stretch on it, just plain old absolute value x. If I stretch this by a factor of 4, when I put in 1 instead of getting out 1, right, if I wrote the equation, it would be 4 absolute value x. So when I put in 1, it's 4 times 1 or 4 times as much. So when I put in 1, I'm going to get out 4 times as much y as I used to. And then, I'll probably not do a good job of drawing this, but it should look something like that. And here, vertically compressed by a factor of 1/3. So again, let me draw kind of the parent function in here. So if we think of compressing this by 1/3, it's hard to, if I compress it by 1/3 right here, because again, this would look like y equals 1/3 absolute value x. If I put in 1, it's 1/3 of 1, and 1/3 is hard to graph. But if I put in 3, 1/3 of 3 would be 1, and that's actually really easy to graph. So if you have a fraction like that, I would think of it, I would put in the value of the denominator so that it comes out to a nice, clean, easy number for graphing. You can also think of this as having a slope of 1/3 and then negative 1/3 on this side. Either one of those versions works well. Let's make that a little smaller again. There we go. So this one's supposed to vertically compress by a factor of 1/4, reflect about the x-axis, shift left 1 and down 2. Okay, so let's go. So that 1/4, if again my regular one goes over 1 and up 1, this one's going to have a slope of 1/4, so it's going to go over 4 and up 1. So that's the shape that I'll draw, but I'll go ahead and go left 1 and down 2. So that's my new vertex. And then I'm supposed to reflect across the x-axis, so that means it's going to open down. And that 1/4, we can think of it as a, oops, I started to think of the word rise, 1/4. We can think of it as rise and run. So we're going to run 4 and then rise 1, and in this case negative 1 because of the reflection. And so this should look something like that, but again, easier to draw on the computer or not using a tablet. Oops. Okay, so that was graphing and transformations. Now we're going to solve equations, and then we're going to solve inequalities. The equations are actually pretty friendly. There's a rule to it, and that is that with any of these, the first thing we're going to do is isolate the absolute value. So if there's stuff going on around the outside of the absolute value, we'd want to simplify that over to the right-hand side of the equal sign. And then it's just going to be whatever's in the absolute value can equal the number, or it can equal the negative of the number. That makes sense if you think of, let me just do an easy one over here, absolute value of x equals 3. Remember, there's two things that make that true, 3, or x could also equal negative 3, right? Because if I put in 3, absolute value of 3 is 3. But if I put in negative 3, absolute value of negative 3 is still 3. So solving that basic setup right there, that's what we're going to do every time. So we just say x plus 6, I either need to figure out what makes that come out to 3, or with x plus 6, what do I put in for that x so that it comes out to negative 3, because either of those options would, when I take the absolute value, make it equal to 3. So for this one, we'll subtract the 6 over, and x equals negative 3. That makes sense if I put it in here. Negative 3 plus 6 would be absolute value of 3 is 3. And this side, subtract that over, and I get I get x equals negative 9. That also makes sense because negative 9 plus 6 would be negative 3, and then absolute value of negative 3 makes 3. And that's pretty much what there is to solving these. The most common issue is people completely ignore this half of the problem. But remember, because it's an absolute value, it has those equal and opposite points on each side of the v, which is what we're seeing here. And if we graph this thing, not that we would probably do it this way, but if we thought of graphing this thing, it would move left 6, because it's a plus 6. So we'll call that 6. And then it would make a V there. Oop, that's a really terrible looking V. And where does this thing equal 3? Which would be that line y equals 3. It would equal 3 when this is negative 3, because it would go over 3 and up 3 to there, or it would go over 3 and up 3 to there, and that's negative 9. So graphically, you're looking for where does this the v intersect the line y equals 3. And so it makes sense that that has to have the two answers, because that's going to happen in two places. For this next one, same basic thing, we just have to isolate first. So let's add the 10 to both sides. And then we have absolute value of 8 minus 10 x. Does not look like an absolute value. Equals 15. And then we just set the argument of the absolute value equal to 15 and negative 15 and solve and see what we get. So minus 10x equals 15, or 8 minus 10x equals negative 15. Subtracting the 8 over, I would get negative 10x equals 15 minus 8 should be 7. And then dividing the 10, we'll have x equals negative 7/10 for a first solution. And same thing on this side, subtracting the 8 over, I get negative 23. And then dividing both sides by negative 10. Negative over negative would be positive, so x equals 23/10. So then solving absolute values with inequalities in them, this is a little trickier. So for here, we have kind of two choices as to what could happen. We can have less thans, or we could have greater thans. For less thans, when we solve the absolute value, we're going to end up with a solution set, because there's going to be a range of values that would make that true. Let's say we had absolute value of x is less than 2, just for instance. if we think about what numbers would make this true, it would be everything from -2 to 2, because all of those values, when you plug them in, are going to come out less than 2. If I put in -3, the absolute value of -3 would make 3, which is not less than 2. Likewise, the 3 wouldn't work out here. But everything between those two values of 2 would come out less than even with the absolute value. What we're seeing is basically if we have a absolute value graph like this and a line right there at 2, where is this graph less than the line equals 2? And it's in between the 2's. It's all in this area where that graph is going to be below the line y equals 2. And so whenever we see a less than, it's going to end up in between those values. So for this one right here, that's a greater than, so we'll do the less than next. For the greater than, it's going to actually do the exact opposite. If I have absolute value of x is greater than 2, and we ask where on this graph is the graph greater than 2, change colors, that's going to be everything on the outside of the 2's. So everything going to the edges. Because if I put in -3, -4, -5, when I take the absolute value, those are all bigger than 2. If I put in, 2.001, that's bigger than 2, 3, 4, 5. And so this, we're going to end up with an interval where there's a union. For the less than, we're going to end up with the interval in between, and that's going to happen every time. When we're looking at these graphs, the graph for less than, and I have them as not equal, so I'll use open dots here, but the graphs for these are always going to look like that, and the interval notation is always going to be some interval AB, with this is A and this is B. For the greater than, these are always going to come out where it goes off into infinity and has an open part in the middle, because we're looking for where is this bigger than that value. So this is always going to take the form -infinity up to A union, again that being B right there, to infinity. And so the way that we set them up is either going to be the argument, if it's less than, is in between the negative and the positive of this value, or if it's greater than, it's going to be less than the negative or greater than the positive. So just like if you kind of follow these two sets of directions, that's going to get you set up correctly. But again, every less than is going to be the closed-in version. Every greater than is going to be the compound version where it has that break in the middle. So let's do some examples with that. This one is a greater than, and so in the event of a greater than, we have x minus 5 is going to be less than -2, so that's giving me this side of it, or x minus 5 is going to be greater than +2, and that's going to give me this side of it. So then we just solve each of these out, so we'll add our 5 over. X is less than 3, or x is greater than 7. And then in interval notation, that would be -infinity up to 3, parenthesis, and then a union there, 7, on out to infinity. The next one will be a less than, and so that's where we set up with the argument of the absolute value in between the two values. So I'll show that next. So here we're going to have -3 is less than 4x plus 5 is less than 3. And then to solve this, this is a continued inequality. If you think of what you would do if this piece of it wasn't here, if it was just 4x plus 5 is less than 3, the first thing you would do is subtract the 5 over. And that's the first thing you do with the continued one. You just have to do it in all three regions. So over here, that's going to give us there we go, negative 8 is less than 4x is less than negative 2, and then we'll divide out the 4 everywhere, same as we would if we just had this piece. But then we get this continued inequality where x is greater than negative 2, but less than negative 1/2. So in other words, the x is in between negative 2 and negative 1/2. And our interval notation for that would look just like that. Scroll down. Same basic thing, we just have a few more pieces around the edges. So for here, we'd want to isolate the absolute value first, same as we did for the equations. So let's go 2 absolute value x minus 3, and we'll subtract that 2 over, and that's going to make this a 4. We'll go minus 2, and then we'll divide the 2 out front on both sides. That's going to give us x minus 3 is greater than 2. So for greater than, it's either x minus 3 is less than the negative of 2, or x minus 3 is greater than the positive side. So remember, the graph goes this way and this way, so we're saying it's either less than the negative or greater than the positive. Add the 3 over, and we have x is less than 1, or add the 3 over, x is greater than 5. So interval notation, negative infinity to 1, everything's parentheses because there's no equals, union 5 to infinity. Oops, and then I did not leave myself any room there, so I'm just going to do, I think I'll erase this one. Set up my next video without leaving myself space. So let me just fix this up real quick. I'll just rewrite that up here. So this is absolute value of 3, x minus 1, plus 2, less than or equal to 11. So we'll subtract our 2 over, still isolating that absolute value first, and that will get us to 9, and then we'll divide both sides by 3, and now our absolute value is isolated. And then this one's a less than, so that means this is going to set up in between the 3's. So we'd have negative 3 is less than or equal to x minus 1 is less than or equal to 3, and then we just add that 1 everywhere. And that gets us to negative 2 is less than x is less than 4. And this time we have equals on there, so we want to use brackets. And negative 2 to 4 would be our solution set. That wraps up absolute values.